In this problem, we would like to discuss the case of a function f that is Lipschitzian mapping, which sends what we're going to show is that the image of a measurable set is a measurable set. So it's properties of Lipschitzian mapping and measurable sets. Okay. So first, let f be a Lipschitzian mapping. So there exists a constant c such that, of course, in the point it says c can be equal to 0, but if c is equal to 0, then what we have, the function is constant, and that's why it's not interesting. The whole problem here is not interesting, because the image of anything is just a point, so it's not interesting. So that's why we're assuming that c is non-equal to 0, such that f of x minus f of y, c times x minus y for every x and y in AB. Lipschitzian mappings are extremely important in applications for the people who are a little bit more aware of stuff like the Banach contraction principle. Then they know that Lipschitzian mappings are a major tool in analysis and advanced analysis. In any case, so first we would like to show that the image of a set of measure 0 has measure 0. So here, let E be a set of measure 0. Then we know that for every epsilon, there exists a sequence of open intervals such that E is in the union of all these intervals, and the sum of the length of these intervals is less than epsilon. Okay, now since f is Lipschitzian, so the condition of Lipschitzian implies that if I is an interval, okay, then f of I is an interval. This is interesting, and the reason is because I is connected, and f being Lipschitzian is continuous, uniformly continuous even, and therefore the image of a connected set is connected, and the only connected sets of are intervals, and that's why the image of an interval is an interval. And this is how we got the intermediate value theorem. In any case, so f of I is an interval, and what's interesting is, and the length of f of I, doesn't matter open, closed, that's not the issue, is going to be less than c, the length of I. Okay? So, in this case, what happened is that f of E will be included in the union of f of In, and the measure of f of E will be less or equal than sigma of the measure of f of In. This is just the subadditivity of the measure. And since the f of In is an interval, then we know the properties of the measure is that this is L of f of In, which is less or equal than sigma of the length of In by Lipschitzian condition, which is going to be less than c times epsilon. So, of course, if we started with epsilon over c, then we'll find epsilon here. So since epsilon was taken arbitrarily small, this will imply that the measure of f of E is equal to 0. Okay? Next, let's take, we want to show that, next, we show that the image of that f of E is an F sigma provided E is an F sigma. So the image of an F sigma is an F sigma. Okay? So let us just say something here about F sigmas of R. If you take any closed set, okay, so let's C be closed set of R, okay, then C is the union of C intersect minus n, okay, and from 1 to infinity, and this is the union of Cn from 1 to infinity. And what can we say about Cn? Cn's are closed because this intersection of two closed sets, and bounded, the Cn's. Therefore, Cn's are compact. So if you want, C is what we shall call K sigma, which is a union, a countable union of compact sets. Okay. Of course, here in the case of our problem, f is only defined on the interval AB. Therefore, we don't have to worry about unbounded. But I'm just giving this as a beautiful, on the side note of this problem, that any closed set, in fact, is a K sigma. It's a countable union of compact sets. And now if you take an F sigma, so in R, so this will imply, because the countable union of countable set is countable, so any F sigma in R is a K sigma. Okay, it's very, very interesting. And of course, if F is continuous and the image of what? Of compact set is compact. This is very important. The image of of closed set may not be closed, but the image of a compact set is compact. So this tells us that F of an F sigma, okay, is an F sigma, and of course this will be done via K sigma because the image of a K sigma is a K sigma. Okay, that's how we will get it. Okay, note that this is not true for closed sets, not true for closed sets. And the best example is to take the arctangent. Okay, so it is Lipschitzian with constant c equal to 1 because the derivative is 1 over 1 plus x squared, which is less or equal than 1, and therefore it is Lipschitzian with constant 1, and the image of R, which is closed, so arctangent of R is equal to minus pi over 2, which is open. So in this case, the image of a closed set is an open set. Okay? Great. So now we want to show that the image of a measurable set is measurable. So let E be a measurable set. Okay? So we know that there exists F in E, which is an F sigma, okay, such that the measure of E minus F is 0. Okay, this is one of the characterizations of measurable sets. Okay, either you find the G delta bigger or an F sigma inside. Okay, so your E, sorry, is equal to F union E minus F. So we have this set has measure 0, and this set is an F sigma. Okay, great. So now F of E is going to be the image of F of F union the image of E minus F. So what did we prove? We proved that this one has measure 0 because the set of measure 0 has an image which has measure 0. And this one is an F sigma. So a union between two measurable sets is measurable. So this tells us that F of E is measurable.